Okay, kiddos, and whoever else may be interested in watching this chemistry and hopefully staying awake, as I'm hoping my kids are, and I'm sure they are because they truly are, MB. So yes. So let's take a look at this next one. We were working on our orbital diagrams. Now you don't want to get these mixed up. The orbital diagrams show the actual lines to depict each individual orbital. Now the next one that we're going to be doing is niobium. Now ideally you would stop the video right now and try to do niobium on your own. Now niobium is element 41. It's one of the transition elements. And so if you want to do that, I'd suggest stopping right now. To element 41, we're talking about neutral substances right now. So we're going to put 41 electrons in. And you'll notice I'm going to obey those rules. 2, 4. Oh, missed some orbitals here. The P should have 3. So that's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, and again this is where 19, 20, we're a little mixed up. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, that little mix up goes there. And now, in order to get those last few in, I actually need my d orbital lines here. Now, some people are going to do circles and squares and a whole variety of things. I do lines. They're slightly more neat. Okay, and now to get to niobium, we have 3 more electrons. And remember, they have to go in within a sublevel. They have to go in unpaired before they pair. So in this case, we have 3 unpaired electrons. And so our answer to this, is it paramagnetic, would be yes. Now, I've begun to introduce you to the concept of electron configurations. So let's write this as an electron configuration. The 1 is the N, the S is the L, and this tells me, that superscript tells me I have 2 electrons in there. 2s2, then we went to 2p6, right? 2, 4, 6. The 6 tells me number of electrons. 3s2, 3p6, 4s2, 3d10. That's unusual. We would have expected it to be the opposite way. And honestly, there are some books that would have put that 3d there. They do it according to energy level. I'm not doing mine according to energy level. I'm doing mine according to energy. So you want to make that distinction. You may see it. It's not that this is wrong per se, although since it's not the way I do it, it must not be right. No, just kidding. The periodic table really gives us according to energy, and I like to do that much better. So we were at 3D, so now we've got to move to our 4P, and I think you will really sink when you are reminded again how we use the periodic table for this. I think it'll click pretty quickly. And then we have 3 electrons in that last sublevel. Now, I want you to remember that if you do want to find out if it's paramagnetic, you really need to at least look at that. Or, you know, if it's got an odd number of electrons there, you kind of know it's paramagnetic. But you really need to draw that outer orbital to find out the number of unpaired electrons. Now let's take a look at what we get from our periodic table. Now, if you notice, remember our S sublevel had 1 orbital that holds 2 electrons. And notice that what do I have in this first block of representative elements? But 2 effectively electrons. As I go from here to here, I've added electrons. Now, that would be S, and so we call this the S block. Now, if we go over to the P block here, you notice that P sublevel has 3 orbitals. 3 orbitals can hold 6 electrons, and lo and behold, we have 1, 2, 3, 4, 5, 6 in that block. So hopefully you're going to be noticing the patterns very quickly. The D sublevel had 5 orbitals, 1, 2, 3, 4, 5, and each can hold 2 electrons, which means we have a total of 10 electrons in a d sublevel. And lo and behold, if we look at the transition elements, you'll note that there are 10 blocks, perfectly matching the d sublevel. So we call this the s block, this the d block, this the p block, and sure enough, the f block has 14 because there are 7 orbitals. Each orbital holds 2 electrons, and if you count across, it would be from 1 to 14. Now, let's take a look at our period number. The group numbers are numbered variously. This is 1, 2, sometimes they go all the way to 13, and other times they'll call this 1A, 2A, 3A, 4A, 5A, all the way 18, excuse me. So, I like to go the 1 to 18 route. Now let's number periods. This is 1, 2, 3, 4, 5, 6, 7. Now, this F block is really popped out in here. Now, some periodic tables show it from here, some from here, and honestly, it gets a little mixed up early on. The electrons start going in, and they don't really know whether they want to be D or F, you know, because it gets to be kind of a maximizing, minimizing balance within that concept. So if we looked at those right in here, we would find they're a little bit what we call irregular configurations. So I'm going to put the period numbers over here as well so that you can match those up. Now, that makes this, by the way, didn't quite finish that thought. Let's finish that thought that we had here. This makes this period 6, period 7. Remember, periods go left to right horizontally. Groups or families go up or down. Now, do you notice, or I hope you notice or remember, because we did this in pre-AP, and most of you caught on pretty quickly, that for our S block, N, the number in front, let me see if I can find a better color for you there, N, our number in front, is equal to the period number. So here I have first period, 1s, second period, 2s, third period, 3s, and so forth on down to 7th period and 7s. Now, if you'll notice over here, we have the same situation. N for our P block is also given by our period number. So this is the first period. Okay, we don't have a 1p. So that's kind of illogical. That's our second 1s electron. This would be 1s1. This would be 1s2. So the p block really doesn't begin until we get to here. So this is really what we would call our p block down below like that. Now, notice that I have second period, 2p. Third period, 3p, fourth period, 4p, fifth period, and so forth. Right? Now, look what happens when we get to the D block here. If you notice a link, we've got period 4 and 3D, period 5 and 4D, period 6. I hope your mind is grasping that pattern right now. We'll see that N is equal to our period number minus 1. So if I'm in period 6 and I'm in the D block, I know all of these elements are going to be ending with 5D. So all the way, this would be 5D10 is what would be represented by that element right there, which is mercury. So it would end in 5D10. So you can plot along, and not only that, you can find elements very quickly from their electron configuration without having to count all the electron superscripts. Now, if you look at the F block, we have the 6th period, and we have 4F, the 7th period, and 5F, and I bet most of you have already guessed that N is equal to our period number minus 2 for our F block. Okay? So that's how the periodic table provides us with the filling order. So let me erase all this so we can do one before this time for this video runs out. and it's already 10 minutes, so that's not much time. So let's try to get one under our belts before I end this video, just to follow our train of thought. So I'm just going to make one up, and you need to be writing it down. I'll be expecting to see that. So what I'd like us to do is antimony, SB. Now antimony is right here on the periodic table. So we're going to take a trip through the periodic table to do the electron configuration. Now we are working still on the ground state. So what we're following here gives us the lowest energy state that maximizes attractions and minimizes repulsions. So let's start at the beginning. It's like taking a walk, and just like a book, we're always going to start left to right. So we'd go 1s2. So we'd write that down, 1s2. Come back to the left. We're not even remotely there yet. 2s2. Cross the ravine. There's no d's here. And then we get to 2p, and we need to go through that whole block, and we're still nowhere near where we need to be. So we need to fill that to 2p6. Wrap around to here, and we would go 4s2. Whoops, I messed up. We're going right here to 3s. Sorry about that. So we're at 3s2. Glad I caught that before we published it wrong, which we've done a couple of times already. 3s2, cross the ravine over here, and we get to our 3p6. Come back here, and we're finally at that 4s2 I tried to do earlier. Now, notice what we do here. It's like taking a little journey, and we have to go down a little hill. So we'd have 3d10. Now we continue our journey because we're not there yet, so I had to fill all the way through 1 through 10. And you notice we kind of come up the hill back, and we're in the 4p6. And the reason I did 6 is we've got to get all the way through this because we're nowhere near our antimony yet. Then we do 5s2, 4d10. I'd go from here to here. Now I'm in the 5p block, 5th period p block, and I'm only going to go in 1, 2, 3 spaces. So I'd have 5p3. Now that gives us antimony, and if you had to identify that electron configuration as antimony, you could add up all these electrons. You could do 2, 4, 10, 12, 18, 20, 30, and so forth, right? You could add them all up and then find out which element has 51 electrons, and indeed that would be antimony. Or you can simply focus on, as long as it's a ground state, that last little address there. So it's 5p, so I know I'm somewhere in the p block. N in the p block is equal to the period number. So now I've identified it to being in this row. And since it's 3, that means I went in 3 spots. So I could identify that as being antimony. Okay, we're going to do a few more of these. So come back and visit.